Hello everybody. Today we're going to discuss inverse trigonometric function integrals. Before we begin, you should recall the following derivative rules dealing with our inverse sine, cosine, tangent, cotangent, secant, and cosecant functions, which we're designating as arcsine and arctangent and so on. In this case, the derivative with respect to x of a arc trigonometric function, the inverse sine of u, is going to be the derivative of u divided by the square root of 1 minus u squared. To find proof of this, you might want to look back into your textbook or into previous videos that discuss this. For the arctangent of u, if we take its derivative with respect to x, we should get the derivative of u with respect to x divided by 1 plus u squared. Of course, for the arcsecant of u, we're going to take its derivative with respect to x as u prime, the derivative of u with respect to x, divided by the absolute value of u, square root of u squared minus 1. For the arc cosine, arc cotangent, and arc cosecant function, we're simply taking the negative of these values. By the way, this will be a reason why you'll see that we only deal with 3 inverse trigonometric function integrals rather than 4. So our arctangent function, for example, if we were to take a derivative of a function like this one using our rules, our derivative following the recipe up here is going to be equal to the derivative with respect to x of the quantity 2x minus 1 to the 1/2 power, and we're going to divide that by 1 plus the square of the quantity 2x minus 1, right? So if we're careful, we should be able to work this one out as our derivative of 2x minus 1 to the 1/2, which is going to be, and I'll just do this separately, 2 divided by 2x minus 1 to the 1/2. Remember that we're taking the derivative of this quantity to the 1/2, so we're going to get 1/2, 2 to the negative 1/2, so that negative 1/2 drops down, times the derivative of 2x minus 1, that's 2. And that's going to be 1 divided by 1 plus, and if we take the square root of 2x minus 1 and square that, we're going to get 2x minus 1. And so rewriting this just a little bit to simplify, the 2 cancels right here, and we're ended up with a derivative that looks like 1 divided by 2x times the square root of 2x minus 1. Interestingly, that looks almost like one of these other ones. So we'll take a look at how we find antiderivatives of things like this, and we'll do that in the future. Here's a quick review right here. So these are our trigonometric integrals that we're going to deal with. The first one deals with arcsine, and it says that anytime we take the derivative of u divided by the square root of a squared minus u squared, we're going to get the arcsine of u divided by whatever that constant a is, plus a constant. For arctangent, when we take our antiderivative, du divided by a squared plus u squared, we're going to get 1 over a times the arctangent of u divided by a plus c. And then finally, when we take our antiderivative of du divided by u square root of u squared minus a squared, it's going to be 1 over a times the arcsecant of the absolute value of u divided by a plus c. In this expression right here, the absolute value does not necessarily have to be in the denominator right here. But u is a differentiable function of x, and a is a constant, a real constant. Any real number will do right here, and we'll show in a further video how we come to that conclusion. One thing I want to do is take a moment, however, and just give you a quick proof on why one of these quantities is true. So let me take on this second one just as an example. How could we prove that this antiderivative is going to fit? If we take the derivative with respect to x with respect to u, of a squared plus u squared. How do we come to this conclusion at all? Well, one thing that we should note is that we can rewrite our denominator right here, and we might say that a squared plus u squared is really going to be the same thing as the antiderivative of du divided by a squared. And if we factor that out, we're going to have 1 plus u squared over a squared. So I'm just going to combine that together and make that u over a quantity squared du. All right, what happens when we take its antiderivative? Well, first of all, we're going to get this constant 1 over a squared, right? Then we have du divided by 1 plus the quantity u over a squared. Now, in order to be able to make this fit with our antiderivative rule, with our derivative rule right here, what we want to do is we want to make sure that we have u prime in the numerator. Well, what do we have? We're going to make another substitution right here. Instead of u, I'm going to call this w. Let's make w equal to u divided by a. What does that make the derivative of u? Well, the derivative of u is going to have to be 1 over a times the derivative of w, which means that we have to take a times the derivative of u to get dw here, right? So that means that, all right, dw, pardon me, here, this is dw and this is du over here. Let me make sure I'm making the right replacement in the right place. Du, there we go. That's a nice du there. Okay, so what's going to happen right here? Well, if we make our replacement, of course, now we have 1 over a, because we're going to take this a constant times dw. So now it's going to be dw divided by 1 plus w squared. And sure enough, that is 1 over a times the arctangent. Arctangent, sometimes a little bit harder to spell than others. Arctangent of, come on, pen. Some days it just doesn't like to cooperate as much as it used to. The arctangent of w plus the constant. Now, if we make our replacement again, we're going to see that this is indeed 1 over a times the arctangent of u over a plus a constant. Now, I'll leave the other proofs up to you as an exercise.